Hello all. We are quite familiar with the space around us. We have some intuitive understanding of the space around us. How do we describe the space around us mathematically? The space is infinite and there are infinite number of points in it. But how do we relate one point to the other? Is there a simple system by which we can describe all of space? Yes, it is there. A mathematical system which describes space is called coordinate system. In this video, we will learn how we transform from one coordinate system to the other coordinate system. What is coordinate system? Basically, it consists of few simple rules which we follow and understand the relationship between the points in space. We are able to describe any point in space relative to any other. That is, we have a simple system of addressing all the points in space relative to some fixed point. The fixed point is called reference point. In this video, we will consider how to describe the points in a plane. If we choose to travel in a single direction, we can move only along a straight path. If we choose to travel in only two directions, the choice is ours when to travel in one direction and when to travel in other direction. But with the two directions, if we choose to travel in only two directions, we can reach the points only in a plane. If we choose to travel in three directions, any one of the three directions may be chosen at a time. Then moving in the three directions will enable us to explore the entire space. We can go from any point to any other point by just choosing to travel in three fixed directions. From the point of beginning, there are infinitely many directions which extend towards different points of space. Though there are infinitely many directions that leads to different points in space, it is possible to choose three simple directions, and we can choose to move only along these three directions and can reach any point in space from a given fixed point or the point of beginning. The point from which we begin or the point relative to which the various points of space are identified is called origin of our coordinate system. In this video, we are going to see how we can describe various points in a plane. And there, we describe the points in a plane in terms of how we have to travel from a certain fixed point to reach any point in the plane. We choose two directions which are mutually perpendicular to each other and a certain fixed point relative to which all other points of the plane will be described. And from that certain reference point, we will describe any point in the plane in terms of the distance we need to travel in the two chosen perpendicular directions. The two mutually perpendicular directions are called x-axis and y-axis. So here we have two mutually perpendicular directions, the x direction and y direction, and they emanate from a fixed point, the reference point called the origin. Now there are infinitely many points in plane, and we have chosen only three entities to describe all the points in plane. One is the origin O, the other is the direction x, and the third one is the y direction. With these three entities alone, we will be able to describe various points in plane. Describing the various points in the plane means we have a system of addressing each point in the plane. Each point can be identified by its own unique address, and that address is formed by referencing to the origin and these two directions x and y. What we have to do, we have to just find out what distance we will have to travel along x and y direction. Any direction may be chosen first to travel. And those distances uniquely define the address of a point to which we reach by traveling in those two directions certain distances. So consider any point in the plane. The point P. We start from the origin and travel a certain distance along x direction and then a certain distance along y direction that reaches to the point P. So we choose first to move in the x direction. So here we go. We move the distance x in the x direction and then we move in a y direction. We have to travel the distance y in y direction to reach the point P. These two distances x and y then characterize the address of point P. These two distances are written as ordered pair xy and they define the address of point P relative to the origin O. The first distance x is the one we travel in the x direction and the second number represents the distance we travel in y direction. That's why we call it the ordered pair of numbers. However, which direction we choose first doesn't matter. But the distances to be traveled in those directions have fixed value. You can choose to first travel in the y direction. You will have to travel exactly the same distance y. And then you can move in the x direction. You have to travel exactly the same distance x. So what order we choose doesn't matter. We can choose any direction first, but the distances we have to travel in those directions remain same. So first number is always the distance in x direction, second number is the distance in y direction. We call this order pair of number xy the coordinates of point P. These coordinates, these order numbers are unique to the point P. So any point in the plane can be described by a pair of number. The first number in the pair refers to the distance in x direction and second number the distance to y direction. If you travel a certain distance in x direction, certain distance in y direction, you will reach a unique point. So it never happens that the two points are identified by the same order or pair of number. Every point has its own unique order or pair of number, and which we may call in our daily language, we may call the order pair of numbers the address of a point P. So this is a mathematical system by which we can identify all the points in a plane by a pair of order numbers x and y. This coordinate system is called rectangular coordinate system or Cartesian coordinate system. In the honor of mathematician René Descartes. Cartesian coordinate system. The mathematician René Descartes, who invented this mathematical system to describe plane. If you want to describe the entire space, we only have to add third perpendicular direction, which we may call z direction. So we may choose a third direction, the z direction, which is perpendicular to both x and y direction. So that direction passes through the screen of the computer. But we shall restrict ourselves only to the two-dimensional plane. Depending upon the nature of problem, often we have to choose specific direction for x and specific direction for y. Here I have chosen horizontal direction for x and vertical direction for y. But depending upon the nature of problem, depending upon the geometry involved, we may prefer to choose other directions for x and y, keeping in mind that they must be mutually perpendicular to each other. So when other directions are considered, the analysis is simplified. But how do we know which choice of x direction and y direction will simplify our analysis? For that purpose, we will need to understand how the coordinates of a point, say P, transform when we switch to another coordinate system where x and y directions are different from these original x and y direction. For example, suppose we have a coordinate system that is simply rotated from this original coordinate system through an angle theta. So shown in red color, x dash and y dash are the new directions for x and y axis. They make an angle of theta with the original xy direction. So shown in red color is another coordinate system. The original coordinate system is shown in blue and the new coordinate system is shown in red. These coordinates x and y are the coordinates relative to the blue coordinate system. The coordinates relative to red coordinate system can be formed in a similar manner. We just have to travel along x dash direction and then y dash direction and have to note down what distances we travel, and those distances will be the coordinates of the same point P in the new coordinate system. Here we go. We travel the distance of x dash in x dash direction and then we travel in y dash direction so that we reach the point P. So these x dash and y dash distances now represent the coordinates of the point P in the new coordinate system, and these two coordinates are equivalent. Xy and x dash y dash are the addresses to the same location but relative to different directions. The origin, however, is same for both the coordinate system. It continues to be the point O. Now we want to understand whether there is any relationship between these new coordinates and old coordinates of the same point. Are there equations which describe the relationship? There are. These equations are called transformation equations. With the help of these equations, we can transform from one coordinate system to the other coordinate system. We can find out the address of particular location knowing its address in a one particular coordinate system. So if you know the coordinates of a point in one coordinate system, with the help of the transformation equation we can find its coordinates in the new coordinate system. So here we proceed to find out the relationship between these new coordinates and old coordinates. X dash is the distance travel along x dash direction. Now when we travel along x dash direction, the distance of x dash, this displacement from origin to the point x dash along x dash direction, this displacement can be represented as a composition of two displacement, one in the original x direction and original y direction. So the displacement x dash is the composition of the two displacement, one in the x direction shown by this yellow arrow, another in y direction. So these two displacement in the original x and y direction constitute the displacement from O to the point x dash. This is a right angle triangle and the displacement from O to x dash forms the diagonal of right angle triangle. Using trigonometry in the triangle OAB, we see that sin theta equal AB upon OB. OB is the distance x dash and therefore the vertical distance OB is equal to x dash sin theta. Similarly, this horizontal distance OA equal x dash cos theta. X dash cos theta and x dash sin theta. By now we have reached the point B. We are yet to reach the point P. So we have been just the part of the way to the point P. To move to the point P, we have to now move along y dash direction, the distance of y dash. Now from B to P, the displacement BP can again be described as the composition of two displacements in the original x and y direction. The displacement BP is equivalent to these two displacements, one along the x direction shown by this yellow arrow, and along original y direction shown by this green arrow. Again, we have a triangle PBQ, which is a right angle triangle. Again, using the trigonometry in the right angle triangle PBQ, we see that BQ, that is the displacement along x direction, it is equal to y dash sine theta, and QP is equal to y dash cos theta. The vertical displacement y dash cos theta. What we have now done, we have described paths leading to the point P from O from two different scenarios. We have two paths from O to B and then B to P along new x and y direction, and our journey from O to P have also been described in terms of the original x and y direction. First we travel from O to B, and this was described as the displacement x dash cos theta in original x direction and x dash sin theta in the original y dash direction. And then from B to P, that is the y dash direction, this displacement was described as the displacement y dash sin theta in the original x direction and y dash cos theta in the original y dash direction. Now the two displacement from OB to BP, these two displacements are equivalent to four displacements in original x and y direction. What is the net displacements in the original x and original y direction? We have seen two displacements in x direction from O to A and then from B to Q. These two displacements in original x direction in our journey toward the point P. So net displacement in x direction is, this is the net displacement in x direction and net displacement in y direction. We can see clearly that the net displacement, the sum of these two displacement in x direction is equal to the displacement x, that is x is equal to x dash cos theta minus y dash sin theta. X dash cos theta, x dash cos theta minus y dash sin theta is equal to x. And similarly, the net displacement in y direction, original y direction, it consists of the two displacement x dash sin theta and y dash cos theta. So net displacement in y direction, original y direction, is simply the y coordinate of the point, and it is equal to y dash cos theta and x dash sin theta. So these two equations are the transformation equations, which gives us the relationship between new coordinates and old coordinates. These equations are called transformation equations. These are the transformation equations in two dimensions for points in plane. For three dimensions, we have to add third direction. What we have done in the present situation, we travel along new x and y directions, and those displacements are expressed as the composition or the sum of displacements along original x and y direction. So when it is about an entire three-dimensional space where we will have three mutually perpendicular directions x, y and z, we derive transformation equations by the similar scheme. We first travel along three mutually perpendicular directions in the new system to reach the point P, and those three displacements in three directions of new system, all those three displacements will be described as the sum of three displacements in the original directions of our coordinate axis, original coordinate system. So in three dimensions we will have three transformation equations, one for x, one for y and one for z, and on the right hand side we will have three terms instead of two terms as seen in the two dimensional case. So these two are transformation equations for two-dimensional plane geometry. Thank you.